All right, so continuing looking at population tests, we have a number of things to look at. First, let's go back to the ideas of a binomial distribution. And we have here a drug company that claims their medicine reduced back pain 76% of patients within 1 hour. And so we're going to think of this as being the success rate. So in a binomial distribution, this is our p-value. So p equals 0.76, because according to the drug company, 76% of the people, independent of one another, have success with this medicine. To test the claim, though, 20 randomly selected patients are asked about their results, and 12 of them reported a reduction of back pain. So what we want to do now is choose an appropriate hypothesis, a null hypothesis, and determine if there's significant evidence to a 10% significance level. If there's significant evidence that we can reject the company's claim. So keep in mind, our null hypothesis will be that the company's claim is correct. We're trying to see if we can reject it. And so let me, erase some of these things here and start by stating our hypotheses. So H naught, that's the status quo, we say, that is assuming that the drug company is correct, because we're trying to see if it is incorrect. So in this case, the null hypothesis is that the probability of success really is 0.76. Therefore, our alternative hypothesis will be that the probability is actually less than 0.76, because we're trying to determine whether there is significant evidence that we can reject the company's claim. And if the company is wrong, that means there's less than a 76% success rate. If there's more than 76% success rate, then the company is still correct, essentially. But we're trying to see, are they wrong? Which in this case is the probability of success less than 76%. So we have a binomial distribution. So I'm going to say X is distributed binomially, in which we have, in this case, 20 trials, 20 people selected randomly, and a 76% success rate. Right? This is what our H naught is based on. So now let's find the probability that of these 20 people, there would be up to 12 people who are successful, that have a reduction in back pain. So I want to find the probability of X being less than or equal to 12. And that means I want to use the binomial cumulative distribution function, which should be rather quick. We have, for this, again, this is all assuming our null hypothesis is correct, so we're using that for our probability, again, that for our number of trials. And we should quickly get a value of about 0.0835, which, keep in mind, is approximately 8.35%. So what does that mean? That means, assuming there really is a 76% success rate with this drug, the probability of us getting up to 12 people who are having better back pain is only 8%. If the success rate really is 76%. That's what it means. There's only an 8 and a bit % probability that we would have a sample of 20 having results like this if their claims are true. Keep in mind, that is less than our significance level. That is less than 10%. And so therefore, we need to reject H naught. We have enough evidence to reject H naught and accept the alternative hypothesis. I keep saying hi. Apparently, I really want to say hello to you. Which therefore implies that it seems that their claim is false. We have enough evidence to state from our 10% significance level that it is false. There is the actual probability of someone having their back pain relieved is less than 76%. Although keep in mind, if we chose a 5% significance level, we would fail to reject H naught. Keep in mind, it's always a bit subjective what significance level we use. All right, with that said here, I have a different question in which an airport has a mean of 29.2 delayed flights per day, but it implements new procedures to reduce the number of delayed flights. After the procedures are fully implemented, we now have 182 delays over a 1 week period, 7 days. So assuming the number of flights follows a Poisson distribution, calculate the p-value, essentially what we figured out up here. But I don't need to do a hypothesis test for this one. So first of all, we want to think about a Poisson distribution. And so I'll write it like this. All we need is the mean rate, which was 29.2 flights per day. However, we want to think about this over the course of a week. So I'm going to scale this up and multiply this by 7. And we get, therefore, our mean being 204.4 delays per week. That's just taking our historical data and scaling it up to a week. So I want to say X is distributed with a Poisson distribution with a mean of 204.4. All right, so this time though, I want to find what's the probability, the p-value, that we would have 182 delays over a week, assuming that the mean has not changed. And so if I was to visualize what's taking place here, a Poisson distribution looks something like this. The mean, again, is right in the middle. In this case, it would be 204.4. We have 182 delays, which is, I don't know, let's say over here, 182 delays. So the question is, what probability is this? Or really, what is the area here? And that is our p-value. The p-value is really this total area that leads us up to that. What is the probability that we would have 182 delays in a week, assuming that the delays still are at the same rate of 29.2 delayed flights per day or 204.4 per week? At this point, it's pretty quick. We want to use the Poisson cumulative distribution function, in which our mean is 204.4 and our X is 182 delays. We should quickly get a p-value of approximately 0.0607, 3 significant figures. That's just our probability, which means if the number of flights per day has not improved, it says they put some new procedures in, but this assumes that because we're using this old mean. So assuming the mean has not improved, then we can assume there is a 6% probability that we would have that. Oh, sorry, do you need to do work on the room right now?
Yeah.
Oh, okay. No, that's all good. I was just recording something. Is it? No, it's all good.
Okay, well, I'm going to the next room for right now. I'll let you do your thing.
Could you do that in about 10, could you come back in like 10 minutes?
Yeah, it's all good, man.
That'd be perfect. Thank you so much. There you go. Just got an exciting little interruption there. I guess I got to finish this in 10 minutes. And so, again, there's no hypothesis test to do here, although we could. But again, it does look like these improvements have worked because there's only a 6% chance that we would actually see this. But there's no significance level given, so we can't say more than that. All right, the clock is ticking. A drug company claims its medicine successfully reduces symptoms within 3 days for 75% of patients. To test this claim, they have 35 patients that are randomly selected and asked about the performance of the medicine. This time we're given the null hypothesis, and that's going to be that the drug company is correct. So that said, determine the minimum number of patients who would have to report an improvement to have no reason to reject the null hypothesis. All right, so we don't actually have to, it's not actually asking for a hypothesis test to be concluded here. We just want to know what would be the minimum number of patients for them to basically accept, or I shouldn't say accept the null hypothesis, but have no reason to reject it. What's the minimum number of patients who can say this drug is working out of the 35? So that the company can, not have a reason to reject their claim. So I want to, again, visualize this distribution. Now, again, hopefully we can start to realize we want to come back to a binomial distribution here because this 75% of patients, that really is our success rate. So I'm going to put the probability as 0.75. And the number of trials, our N, is going to be 35 because there's 35 patients we're looking at here. And so if I think about my binomial distribution, it always has a shape roughly like this, although it is discrete, not continuous. If we want to, now at some point, what's the minimum point? Let's say right here. What value would have to go here so that this region is 5% or less of the entire shape? So the area of this would be 0.05 at most. what number would have to go there for a binomial distribution? So one thing we can do then is, because we know all other aspects of this binomial distribution, we know it's a binomial distribution, we know the number of trials, we know the success rate. What would lead, what would be our x value? How many would have to be successful for this to be at most 5%? Well, we could use our inverse binomial CDF. We got to be a little bit careful though. If you do that, you should really quickly, and for this though, we would say the area we want to find is 0.05, right? That's the area we're looking at. We should really quickly, if we do that, it should almost right away give us, come back. It should right away give us an x value of 22. So it's saying that 22 is the nearest value to 5%. But it may not be, just because it's the nearest, it may not be the best for our question. So I'm going to go with that, but let's double check a few things. So we know it's going to be around 22, but depending on the context of the question, we always want to check a few things. So here, I'm going to just use the usual binomial, not the inverse, cumulative distribution function. And if we find the probability that x is less than or equal to 22, we get probability of that of about 0.0756. Notice it's more than 5%, and that's because binomial distributions are discrete. It's going to be 21, 22, 23, not something in between. So let's just double check and see what we would get if we go x, the probability of being 21. What if we had 21 people who reported success? That'd be only a 3% probability. And so we want to find the smallest number that would still show us that we should not reject the null hypothesis. So if you look at this one here, 21, if there were only 21 patients who reported success, then we do have enough of a basis here to say we should reject the null hypothesis because we're under 5%. But if we look at this one, we are just barely within the zone. And so from the drug company standpoint, as long as there are 22 or more patients who can report an improvement, then we don't have a reason to reject their hypothesis that their drug really does work at 75%. So, long story short, 22. So 22 patients is the minimum. Ideally, if their drug really does work, they'll get more than 22. All right, lastly, we want to look at a new type of test to determine how likely a particular correlation might come up. So here we have an experiment, this table showing the reaction times between two people. And we want to realize, okay, so we can draw conclusions about the correlation of the sample, but this is just a sample. There's a chance that sample is giving us a correlation that is just happening by fluke, or there's a probability it's giving us, depending on the samples chosen, is a chance that the correlation we see here is artificially high or low compared to the actual population. In this case, all population would be all possible samples you could take from these two people, which we can't really do. So with that said, how do we approach a question like this? How do we determine at a 5% significance level whether there really is a positive correlation? So I would say first thing I would do is just graph this in your GDC, make a scatter plot, and you'll see it does seem to form a positive correlation, and you could find linear regression. However, that's not the purpose of this, because this is just a sample. And that sample we see, even though it does seem like a linear correlation, that could just have occurred by coincidence. There's a probability that if we took more points, that there actually is no correlation, or there's not a positive correlation, and just this sample just happens to show that there is a positive correlation. So what's the probability that we would get a correlation like this, a positive correlation, if in reality there actually is no correlation? That's how these type of questions are set up. And so all these questions have the same null hypothesis. The null hypothesis is that rho, Greek letter rho, not p, looks like p, is 0. So that row, that Greek letter row, represents the correlation of the population. And for these questions, the null hypothesis is always assuming the null hypothesis. There is no correlation in the actual population. Sorry, my throat is dry. So we want to see, though, okay, that's our null hypothesis. There is no correlation between this data. That's it. Our alternative hypothesis is that there is a positive correlation. Like I said, if you make a scatter plot of this, it does seem to have a positive correlation. So what's the probability that we would get a positive correlation if this actually has no correlation, right? So questions like this is where we want to use a linear regression t-test. First thing you do, well, hopefully you would already have this data into your table, and then find that probability. And we want to do a t-test where we want to state, we're trying to find what's the probability that we'd have a positive correlation. And you should really quickly get a p-value of about 0.00595, which, keep in mind, is approximately 0.6%, which means if there really is no correlation between Matt and Evelyn's reaction times, if we took many more samples, an infinite number of samples, and there really was no correlation, then results like this that have a positive correlation, we would expect to see less than 1% of the time. That's a pretty small probability, and it's far smaller than our significance level. This is far smaller than 5%. And so that means we can reject H0 and accept H1. That there does seem to be a good statistical basis to say that not only is a sample showing a positive correlation, but that there probably really is a positive correlation among the samples. So we are going to accept this test here. Whew. Okay, I got it done before the workers are coming back in. I'm going to stop before they kick me out.